We've said before that the columns of a transformation matrix are the axes of the new basis vectors of the mapping in my coordinate system. We're now going to spend a little while looking at how to transform a vector from one set of basis vectors to another. Let's say I have two new basis vectors that describe the world of Panda Bear here, and Panda's world is orange. So Panda's got first a basis vector there, and then another basis vector there, say. And let's say in my world, Panda Bear's basis vectors are at 3, 1 and are at 1, 1. And my basis vectors here are E1 hat equals 0, 1 for E2 hat, and E1 hat is equal to 1, 0. So those are my basis vectors, and the orange ones are Panda's basis vectors. Now, and so Panda's basis vectors, the first one for Panda is his 1, 0, and the second one is 0, 1 in Panda's world. So Bear's basis vectors are 3, 1 and 1, 1 in my blue frame. That is, I can write down Bear's transformation matrix as 3, 1, 1, 1. Now, let's take some vector I want to transform. Let's say that vector is, in Bear's world, is the vector a half of 3, 1 in Bear's world. So it's 3 over 2, 1 over 2. So the instruction there is do 3 over 2 of 3, 1, and then do 1 over 2, a half of 1, 1, in my frame, if you like. So in my world, that's going to give me the answer of 3 times 3 over 2 plus 1 times 1 over 2 is 9, 10 halves, which is 5. And 1 times 3 over 2 plus 1 times a half, so that's a total of 2. So that's the vector 5, 2 in my world. 5, 2. Those two are the same things. So this is Bear's vector, and this is my vector. So this transformation matrix here are Bear's basis in my coordinates, in my coordinate system. So that transforms Bear's vectors into my world, which is a bit of a problem. You know, usually I'd want to translate my world into Bear's world. So we need to figure out how to go the other way. So my next question is, how do I perform that reverse process? Well, it's going to involve the inverse. So if I call Bear's transformation matrix B, I'm going to want B inverse, which is b to the minus 1. And the inverse of this matrix, well, it's actually pretty easy. We can write down the inverse of that matrix pretty easily. It's going to be a half of 1, 3, flip the elements on the leading diagonal, and put a minus on the off-diagonal terms. And we can see the determinant of that's 3 minus 1 is 2, so we divide by the determinant as a half. So that's going to be b to the minus 1. And that's the my basis vectors in Bear's coordinates. So that's my basis in Bear's world. So my 1, 0 is going to be a half of 1 minus 1 in Bear's system, and my 0, 1 is going to be a half of minus 1, 3 in Bear's system. And we can verify that this is true if we take this guy, a half 1 minus 1, and compose it with Bear's vectors. We've got 1 plus minus 1 of those is going to give me 3 plus 1 is 3 minus 1 is 2, 1 minus 1 is 0, so that's 2, 0, halve it, gives you 1, 0. So that really does work. If I take a half 1 minus 1 of Bear's vectors, I get my unit vector. Okay, so that really does do the reverse thing. So then if I take my vector, which was 5, 2, and then I do that sum, I should get the world in Bear's basis. So I've got 5 times a half minus a half, using that guy, plus 2 times minus 1, 3, and that will give me a half of 3, 2, when I multiply it all out. And if I do the same thing here, I've got 5 times 1 minus 1 times 2 gives me 3 over 2, gives me 3 over 2. It all works out. If you do it that way, or if you do it that way, you still get that answer. So that's Bear's vector, again, which is the vector we started out with. So that's how you do the reverse process. You need to, if you want to take Bear's vector into my world, you need Bear's basis in my coordinate frame. And if you want to do the reverse process, you want my basis in Bear's coordinate frame. That's probably quite counterintuitive. So let's try another example where this time Bear's world is going to be an orthonormal basis vector set. So here's our basis vectors at 1, 0 and 0, 1 in my world in blue. And Bear's world is in orange. Bear's world has 1, 1 times, and I've made it unit length, so it's 1 over root 2, and minus 1, 1. Again, the unit lengths are 1 over root 2, so they're those two. And those you can do a dot product and verify that those two are at 90 degrees to each other. And they're Bear's vectors 1, 0 and 0, 1. So then I can write down Bear's transformation matrix that transforms a vector of Bear's. Now, if I've got the vector in Bear's world that's 2, 1, then I can write that down. And I will therefore get the vector in my world. So when I multiply that out, what I get is I'll get 1 over root 2 times 2 minus 1, which is 1. And then 1 times 2 plus 1 times 1 gives me 3. So in my world, the vector is, as I've written down, 1 over root 2 times 1, 3. So if I want to do the reverse transformation, I need b to the minus 1. And b to the minus 1 is actually quite easy. Because this is an orthonormal basis, the determinant of this matrix is 1. So it all becomes quite easy. So I just get 1 over root 2, keep the leading terms the same, flip the sign of the off-diagonal terms because it's a 2 by 2 matrix, so it's really simple. And if you go and put that in, if you say, if I take 1 over root 2 times 1 minus 1, so I take one of those plus one of those, multiplied by root 2, I do in fact get 1, 0, and the same for 0, 1. It all works. So then if I take the vector in my world, this vector in my world, which is 1, 3, and multiply it out, then what I get is the vector in Bear's world. So that's 1 plus 3, which is 4, minus 1 plus 3 is 2, and I've got 1 over root 2 times 1 over root 2, so that's a half. So in Bear's world, this vector is 2, 1, which is what we originally said, so it really works. Now this was all prep really for the fun part, which is, we said before in the vectors module that we could do this just by using projections if the new basis vectors were orthogonal, which these are. So let's see how this works with projections. So let's try it with projections. What we said before was that if I take my version of the vector and dot it with Bear's axis, so the first of Bear's axes is that in my world, then I will get the answer of the vector in Bear's world. So that gives me 1 over root 2 times 1 over root 2, which is a half, of 1 plus 3, which is 4. So that gives me 2. And that's going to be the first component of Bear's vector because it's the first of Bear's axes. And I can do it again with the other of Bear's axes. So that's 1 over root 2, 1, 3. That's the vector in my world, with the other of Bear's axes, which is 1 over root 2 times minus 1, 1. And when I do that dot product, what I'll get, 1 over root 2's will multiply to give me a half again, and I've got 1 times minus 1 plus 3 times 1 is a total of 2, which is 1. And that's Bayes' vector, notice, 2, 1. So I've used projections here to translate my vector to Bayes' vector just using the dot product. Now remember, with the vector product, what I'd have to do is I'd have to remember to normalize when I did the multiplication by Bayes' vectors. I'd have to normalize by their lengths, but in this case their lengths are 1. So it's actually really easy. So we don't have to do the complicated matrix maths. We can just use the dot product if Bayes' vectors are orthogonal. Now there is one last thing. If you try this with the example we did before, with Bayes' vectors of 3, 1 and 1, 1, so before we had those being Bayes' vectors, if you try the dot product with those, because they're not orthogonal to each other, it won't work. And give it a go for yourself and verify that it really won't work, that they need to be orthogonal for this to work. If you have them not being orthogonal, you can still do it with the matrix transformation, you just can't do it with the dot product.